And then I will give you some time to work on a couple of these assignments. So getting back then to chapter 4, let me, and again, feel free to open these notes. Feel free to make a copy and feel free to do whatever you want on those. Of course, you should be working through chapter 4 in the textbook and chapter 19. We're going to start in on chapter 19. I'm going to give you a couple of assignments related to chapter 19 today, as a matter of fact. So just quickly, yesterday I mentioned this ideal gas law, PV equals nRT, and it is one example from your chemistry class that we can actually apply to real life, how air moves through the atmosphere, both horizontally and vertically. And I want to really emphasize this concept of air moving vertically, because when we go outside, we think of wind as this horizontal component of the air, because that's what we feel. We feel the wind blowing against us. We see trees moving. And so we think of wind as being this horizontal um, thing. But the vertical movement of air actually plays a very, very important role, not only in the weather and climate that we experience, but also on a larger scale. What you're going to see at the end of chapter 4 are these biomes and these worldwide pattern that we see in the location of these biomes. And so I want you to remember that. And this is applicable, especially when we talk about this concept of the relationship between the temperature of the air and pressure. And very commonly as kids, you hear warm air rises. You'll still hear people talk about this idea that air moves from warm toward cold. And there's some truth to that. But if you're really a meteorologist, then you talk about this concept of pressure gradients, okay? How pressure changes horizontally and vertically, and the role that those pressure gradients play in the movement of air. And so we know that air moves from areas of high pressure toward areas of low pressure. So I want you to kind of stick that in the back of your head. And also just remember this relationship between pressure and temperature. If one goes up, the other goes up. If one goes down, the other one goes down. We talked about this stuff yesterday. I want to give you some applications of this today. This idea that there is this effect called adiabatic cooling. As you move a volume of air through the atmosphere vertically, the cooling is a result of the reduction in pressure. Also, the fact that you're moving away from the source of heat. Remember, the sun is not the direct source of heat for the troposphere, the lower part of the atmosphere. The Earth is the source of heat. The sun's radiation passes through almost every gas in our atmosphere. Ozone is the notable exception. Ozone is found in the stratosphere, and we'll see how that impacts the movement of weather here in a minute. So adiabatic cooling and heating is really important. As you move an air mass higher in the atmosphere, the cooling effect is important, because what that's going to do is lead to condensation. If you take a volume of air that has water vapor, if you want to turn that vapor into a liquid, you just cool the volume of air. As you cool that volume of air, the vapor condenses into a liquid. If there's enough liquid, it forms clouds. If there's an even more liquid, then it starts to rain. And so, as we see this rising air pattern develop around the planet, we can start to predict those areas that are going to experience the most rainfall. And then the opposite, where we see this adiabatic heating, or air that tends to fall from higher levels in the atmosphere to lower levels, all the way to the ground, we're going to see air that is being heated as pressure increases toward the surface of the ground, and you never get condensation in a volume of air when the air is heated. And the reason this is important is because that is where we're going to find, on a large scale, the location of the deserts on our planet. The last little bullet point says latent heat. I want to just quickly focus on this for just a second. I have a beaker here, everyone, with some water in it. Now, if I want this water to evaporate, and I want to evaporate this water quickly, I can do that by adding energy. Okay. And so if I want to evaporate that water, I can get out my hot plate. I plug the hot plate in. I turn it on. I put this beaker on the hot plate and I watch the water turn to vapor, liquid water turn to vapor. Eventually, the whole thing would evaporate and I would be left with an empty beaker. Okay. So, the reason this is important, everyone, in chapter 1, or maybe it was 2, I guess chapter 2, we saw this concept of the thermal dynamic laws of thermodynamics. And one of those laws was this idea that energy, and you could also apply it to matter or mass, energy is never created nor destroyed. And so if I have liquid water and I add energy in the form of heat to the water to evaporate it, what happens to all of that energy? What happens to all the energy that I used to evaporate the water? It doesn't go away. We don't use it up. Okay. It is transferred into the vapor of the water. We call this latent heat. Okay. So any process that involves energy to change a substance from one phase to another phase, liquid to a gas, then that energy is stored in that higher phase. The energy is released when you step back the other direction. So if I use energy to evaporate water, turn it to a gas, when I turn that gas back to a liquid, all of the energy necessary in the original evaporation process is then released. Okay, and this is really important. We're going to see why in just a second. Okay. All right, let's talk about these convection currents. I showed you this yesterday, and this is a process that we have to understand both locally and on a large scale. Morning comes, it's a nice sunny day. The sun shines, the sun's rays pass right through our atmosphere. The sun's solar radiation heats the planet warms up. That warming planet then re-emits radiation in the infrared wavelength. Just so happens that carbon dioxide is really good at absorbing that particular wavelength, and the air right above the Earth starts to heat up. As you raise the temperature, the pressure then also goes up, and that volume of air begins to move upward. Why does it move upward? Because the temperature and the pressure of that volume of air is higher than the pressure of the air above it. So as soon as you have the heating of the surface, then that air begins to move upward. Okay. Now, we mentioned in some cases that upward moving air will cool. It holds enough volume of water vapor. That vapor begins to condense, turn to clouds, and then eventually turns to rain. At some point, that air is going to reach a ceiling. And we said that ceiling was determined by this inversion layer. So that volume of air under greater pressure than the air above it will continue to rise until it reaches this point in the stratosphere, the lower stratosphere, where the ozone absorption of ultraviolet rays heats up the ozone and actually puts that particular layer under more pressure than the air below it. That marks the ceiling of the troposphere. Okay. And so this convection current system here is going to account for a very large scale pattern that we see on our planet. And one of the things that you have to be aware of on any given day of the year is where the sun is the most directly overhead on planet Earth. And that will migrate between 23.5 degrees north latitude and 23.5 degrees south latitude. Okay. If you want to see the sun directly over your head, you have to go to a minimum of 23.5 degrees north latitude or 23.5 degrees south latitude. Okay. So we never see the sun overhead in Verona. It always has some component of south. And so what we're going to do now is we're going to apply this pattern of convection current where you have heating of the earth, heating of the air above the earth. That air rises, the air condenses, in some cases forms a cloud and rain. As it continues to rise, eventually it hits the stratosphere. That air then starts to move horizontally. As it moves horizontally along the bottom of the stratosphere, the top of the troposphere, it cools. And at some distance from the rising point, it begins to fall. As it falls, you'll have air that is moving in toward the high pressure zone to replace the air that is rising. And you end up with this cell or this convection current that is a cycle. Okay. So there's one other little piece here that we have to add to this. But I want to take a look at this here for a second. This is the equator, and you see this term ITCZ, and that is a term that refers to the point where the sun is directly overhead. Intertropical convergence zone. So on any given day of the year, you could find a location by latitude where the sun is directly overhead. That is where the most direct solar radiation is received on the planet. And that's going to be the position where this convection current originates. Okay, that's why that's important. And so what we see then is where we have that ITCZ, we're going to have rising air and we're going to have clouds forming just about every single day. All right. So, and this occurs in the tropics. The tropics are defined as that latitude between 23.5 degrees north and 23.5 degrees south. And that ITCZ line is going to migrate throughout the year between those latitudes. And so between those latitudes, that's where you're going to have the most predictable, the most consistent convection cells occurring and forming, and you're going to have the most consistent and predictable rainfall. Now, you all know that. In most cases, when you say the word tropical associated with any type of a biome, in your head, the first thing you should think of is lots of rainfall. And we know the tropical rainforest is located in within this particular latitude range that is characterized by high amounts of rainfall. And the reason, this is where the most direct solar radiation is occurring. That's where the rising air is most commonly found. Now, at that particular location, what you're going to see then at the ceiling is air moving horizontally north and south. At some point, about 30 degrees, the air is going to fall. Where that air is falling, you have warm air, you have dry air. That is the location then of the largest deserts on our planet. So wherever we see these cells, these convection cells occurring, if we can identify the location of the falling air, we can identify the location of the deserts. Now, one thing I want you to notice here, when you look at this horizontal movement, what we should see is a north-south movement from about 25-ish degrees north latitude back toward the ITCZ or the equator. We should see air that is moving directly north-south. But instead, what we see is a veering of the air. The air appears to curve. Okay. And the same thing happens if we move north from 23.5 degrees. Instead of the air moving from south to north toward the rising air, instead, what we see is the air tends to veer to the right. And so I'd like to take a moment and talk about that particular phenomenon. It's known as the Coriolis Effect. And the thing that happens on planet Earth that is very significant is the spinning of the Earth. And anything that is traveling above the surface of the Earth is traveling in space while the solid Earth is spinning below it. So imagine for a moment you're standing on the North Pole and you've got a rocket of an arm. You're holding a baseball and you want to throw that baseball directly to Verona, Wisconsin. You're on the North Pole. You're going to throw that baseball directly to Verona, Wisconsin. Where do you aim? Do you aim right for Verona, Wisconsin? If you aim for Verona, Wisconsin, in the amount of time it takes for that ball to leave your hand and travel all the way to Verona, Wisconsin, the Earth has moved below that ball. And so instead of the ball landing where you aimed it in Verona, it's going to land somewhere slightly to the west. This is known as the Coriolis Effect. Now, one thing to keep in mind, this is an effect. The ball itself is in fact traveling in a straight line. It appears to be moving or veering off to the right because the Earth has moved underneath it. This Coriolis effect, by the way, was really highlighted during World War II. Very commonly, scientific discoveries happen at times of war. And World War II, we developed ways to attack each other involving long-range artillery and missiles. And that artillery, that would be, you could shoot artillery from a battleship, and that artillery would travel 2, 3, 4 miles to its target. And what they discovered was that they would never hit the target. And they figured out that in the time it took, even to travel a couple of miles, the Earth had moved enough under the artillery so that they would not hit the target. I have a friend who is really into target practice. He's not doesn't hunt, but he has a high-powered rifle, never leaves the gun range. He's into competition target practice, target shooting. And his high-powered rifle, he will fire on targets that are over 1,000 yards away. And in the time it takes for the bullet to leave his gun and strike the target, the Earth has moved enough underneath that bullet so that if he does not compensate for that movement, he will not hit his target. Okay. And so this is a very real effect. And it has the effect of veering things in the northern hemisphere, deflecting them to the right. So if we start at 30 degrees north latitude, like in this picture here, and we shoot something off to the north, it's going to appear to deflect to the right. And the same thing if we're headed south. Now, this is important because we know in Wisconsin, our weather tends to come from the west. If we look at what we call the jet stream represents that air that is moving horizontally to replace the air that is moving aloft in these large scale convection currents. And so if we look at this map, where is it? If we look at this map, that air should be moving from approximately 25-ish degrees to approximately 75, 70-ish degrees. It should be moving from the south to the north. But instead, it veers to the right. And so when we look at the weather that tends to influence on a regular basis North America, where we live, the United States, that weather tends to move from the west across the country toward the east. And that is a result of this deflection. Okay. And so it plays a very important role, the Coriolis effect. Whew. Well, let's see. Is there anything else here? want to show you one other thing. I'm going to show you one thing here. This will just take like a second. I want to actually show you this in action here.
Blue skies soar over an
So
increasingly
check this out,
electric
everyone.
atmosphere.
I'm going to fast forward to this part right here. Okay, so this is something that we see commonly in and around Verona. Usually sometime around April, April, May, we can start getting those big thunderstorms and then right into the hottest part of the summer. And this is a phenomenon in late July, August that you can observe in some cases almost daily. And so think about what's happening here. This is on a small local scale. What we just talked about happening on a larger scale across this entire tropical zone. We start out in the morning and it's nice, clear, beautiful, sunny summer day, but it's humid. The air has a lot of moisture in it. Okay. It's one of those hot August humid days. Starts out sunny. And then somewhere around 11, 12 o'clock, you start to see these little clouds appearing. The earth is heating up. That earth is causing differences in pressure. In some cases, the atmosphere is under more pressure at the surface than aloft. That air starts to rise. As it's rising, okay, all of that vapor that's stuck in the atmosphere is turning back into a liquid. Every time you get water condensing into a liquid, it releases that latent heat. All the heat that went into evaporating this water is released. And it's somewhere around 600 calories per gram. That's a lot. Okay. That's a lot. And so now you have a feedback loop. You have vapor that's condensing to a liquid. But when it condenses to a liquid, it releases tremendous amounts of heat. That can actually evaporate the liquid that just condensed. Okay. And it causes it to be under more pressure. The temperature goes up when that energy is released. More pressure causes it to rise some more. As it rises, it condenses, it releases the heat, evaporating, condensing, and it's this cycle of condensation and evaporation, releasing all this heat. And so what we see are these big thunderstorm clouds, and you can almost see them billowing upward. Um, and then eventually they reach a ceiling. The ceiling that you see right here, that is the top of the troposphere. That represents the bottom of the stratosphere. And you can actually see it. You can see where that ozone layer exists in the atmosphere because the clouds stop right there. Okay. Now, as kind of an aside, but related topic, when we talk about hurricanes, very, very commonly in our part of the world, hurricanes will form as thunderstorms off the coast, the west coast of Africa. And as those thunderstorms are moving out over that moist Atlantic Ocean in the middle of the summer, they start to approach the warm water currents coming from the tropics. And it's that warm water that evaporates, and the energy that is stored in that water vapor is what drives the power in the hurricanes. Okay. So as that warm water is condensing, the energy that is released into that thunderstorm system is what causes that thunderstorm to grow in strength into a hurricane. And the worst hurricanes are the ones that occur over the warmest water. If you want to kill a hurricane, just push it north into the cold Atlantic or push it over land where it's not fed that warm evaporating water. So watch this. This is just 10 seconds here, 20 seconds, and you'll see this process in fast motion. You can see the condensation and the billowing of this cloud upward. This is fast motion, of course,
The explosive
but
updrafts
I'm
rushing
willing
into
to
the city.
bet that most of you have seen this occur um, just any summer day in southern Wisconsin, those hot, humid summer days. And then the top, of course, marks the location of the top of the troposphere. And then eventually the condensation is sufficient enough to form precipitation. And so, very commonly in the summer, you will hear meteorologists predict a hot summer day and the chance of a thunderstorm. It's going to be 85 today, humid, chance of thunderstorm in the afternoon. All right, I'm done, everyone, for now. I was going to talk to you a little bit about these low and high pressure systems, but it's really the same concept. If you have high pressure, air moves from high toward the low. So if the pressure is 1026, that's millibars, the air is going to move outward toward the low. It's veered to the right by the Coriolis effect. And so you have this typical spiral motion around a high pressure system. If you hear Bob Lindmeier talk about a high pressure system, that means that the air tends to be falling and moving outward from that system. If you hear Bob Lindmeier talking about a low pressure system, then that means the pressure is going to be higher outside of the system. The air is going to move from the high pressure outward toward the center. When it reaches the center, it will move upward because it has nowhere to go. It can't go down. If you have upward moving air, you're going to have condensation, cloud formation, you're going to have rain. And these can be very large. These can cover entire states, these pressure systems. The reason this is important to us, where's my annotation thing here? Okay. This is why it's important, everybody. I can do this in like a second here. If you have, let's say you have, I don't know, let's just look at this for a second. Let's say you have, I don't know, let's say you have a high pressure system for this one. And let's say you have a big H centered right here. Here's a high pressure system. That means the air is going to be moving like this out of that high pressure system, outward and clockwise. Okay. So, what does that mean for Wisconsin? That means this warm tropical air that's centered over the Gulf of Mexico is going to be heading toward Wisconsin. That means if you live in Wisconsin and you have a high pressure system to the west of Florida, that high pressure system is going to push warm, moist air toward Wisconsin. We're going to have southerly winds. Those winds are going to feel warm, and there's a good chance that air will condense into storm clouds at some point. All right, I'm done. I know I talk too much. There's a lot in this chapter, though, everyone. We haven't even talked about the rain shadow yet. We'll do that another time, though. Okay, tomorrow I am not